So, what we're planning on going through today is something called binary search and linear search. And this is I guess this is officially like the last thing you learn, but it's basically just how to search an array for a specific value, right? And you can do this with an array. You can also do this with a what's it called? A vector. Same idea. But there's basically two algorithms, right? An algorithm is simply just a set of steps, one technique, and then there's another technique, and nothing too complicated than that. But the first technique is going to be linear search, and linear search is pretty dang simple. In fact, it's like a function called linear search. So we'll make a function called linear search, and we want it to make a boolean, right? We want to keep a boolean because if it has the value, if our array has the value that we're looking for, then this function should just return true. And if it doesn't have the value that we're looking for, then we'll have it return false. So we'll make a function boolean type, and we'll call it linear search. And we can make the first parameter an array, right? So we'll make an array. So we'll call it int array that. There we go. And then we're going to do our linear search. So basically, we're going to say, I'll first return false. By default, we would return false because that's what we would assume. Is we don't assume that the key that the value that we're looking for is in the array until we actually find it. But before that, we'll have all our code. So basically, we have our array. We also need our key, actually. We need to have another parameter for the value we are looking for, which we typically call the key, right? So let's say this array would be specifically for integers if you were dealing with an array of integers and you had an integer that you were looking for. So we'll call it integer key. And then we're going to say something like, and one more thing, actually. If you have an array, you're going to have to pass a size into, so int size. So you'd have, for an array, you'd have 3. If you were to convert this function to take in a vector, you'd only need 2 parameters. So we have for, let's create a for loop. We're just going to say for int I equals 0, I less than size, I plus plus. Okay. So now, basically, we're just creating a loop that's going to run as many times as we have values in our array. Pretty simple. And all we're going to do here is create an if statement. We're going to say if array at index I equals key, and we're going to say return true. And that's the linear search, basically, just right there. This whole thing should return true if we have our key in our array, and false if not. So we just have our for loop. That's going to go through every element of our array using index I, because index I will go from 0 till the size of the array. And so it's going to check it, and it's going to check each element. It's going to see if it equals our key, then that means we found our key in our array. And we would say return true, right? So let's see if this works real quick. Let's say we have an array. Yeah, let's call it int list of nums. And we'll say it has a const int size equals, say 100. size. After this, we're going to say something like, let's initialize all of them, actually. Let's initialize all of them to some random number. So we're going to say sran times 0. That'll let us do random numbers. We're going to say int I equals 0, I less than size. Strange. Okay. I plus plus, so that we have an array that's going to run 100 times basically. Or sorry, not an array, but a loop, right? And then in here we're just going to initialize each element. So we'll say list of nums at I equals rand. So our rand function, that'll generate a random number, but then we can control it. We'll make sure that it only does between numbers 0 and 100. Sorry, 0 and 99. And then we'll add 1 to it, so we get 1 to 100. Right, so now this should allow us to get numbers from 1 to 100 randomly. Now, what we can do, we can maybe print our, right, let's just do it in the same thing. We could just say cout, we'll list out, we'll print that specific value out, and then we'll do a space in between each one. Actually, we'll do a tab in between each one. So, if we say 4, now what we can do is we can say if linear search, right? We're going to we call our linear search function. So we're going to say if linear search, and then we're going to pass. The first thing it tells us we need to pass our array. So our array is list of nums. So we're going to pass that into this function. Now, whenever you pass an array into the function, you only have to pass the name. You don't actually have to like pass the bracket stuff. You just have to pass the names, and that should be fine. Then we want to pass, of course, the size. And then we need to pass what we're looking for. So we can say we're looking for the number 40, right? Maybe that's our key. That's the number we want. Now, if this function ends up returning false, this code will not run. Whatever in the if statement will not run. But if it returns true, we can say something like cout, the value was found. And that should be good enough to kind of get things started. So let's actually see. I think it's Control-Shift-B. There we go. So let's see if this works. Temp. All right, so here's our array. And it says the value was found at the very end. So 40 was found in here somewhere. I don't know if I can see it with my own eyes, but let's see. I mean, I guess I believe him. I'd like to see it though. Fine. So it says it was here. Let's actually make a way so that way we could see it. This starts to actually become where it's like, okay, well, you need a little bit more information than just I found it. Sometimes you'd actually like to know where you found it. So what we can do, let's actually do this. When we output each element in our array, we'll also input the index right next to it. So we'll say something like the index. We'll say I. And then the value. So now let's see this. Okay. So, kind of good. Wish it was a little bit nicer, but fine. So it says the value was found again. So as you can see right here, actually, I'll put it on space, but basically what it is just going to be the index right next to the value. Okay, and I would say, I'm going to do a little formatting right here just to make it look a little bit better. So if I divisible by, I don't know, 13 equals 0. So basically what I'm doing here is I'm just making it so that way, oh, whoopsie, I don't need that right there. I need that right here. There we go. I'm just making it so that every about 13 numbers, it's going to create a new line, which is what I'm going to do right here. So cout and L. So now let's see it one more time, but with the new formatting. So there we go. Now it's much more. It's like controlled how far it goes out. So we can see 0 had the number 35. Actually should +1 this. I can see index number 47 had the value 96, and so on. So now, another thing I could do is maybe, let's say maybe what I could do is instead of returning true or false, what I could do is maybe return an integer. So let's change our return type of our function to int. And instead of returning, on default, we don't want to return 0, right? We don't want to return 0 on default. In the case like we have a failure, what number should we return? So let's not return default. Let's not return 0 because 0 is an index, right? If I return 0, then it would probably say, oh, it's at index 0. But that's not what we want. What we want it to return -1, probably. We'll say -1 because obviously -1 cannot be an index. And then if we do have a good number, like if we find it, we'll just return the index, which is I, whatever I is at that moment when we find it, right? So it'll return I. But then we have to change our little if statement down here. And instead of saying if this returns false, we just got to say if linear search with all these parameters returns the value, and we'll say equals -1. If the value returned ends up equaling -1, then we didn't, sorry, not -1. We have to say if it doesn't equal -1. Yeah, you could say that, or you could say just greater than -1. But we'll say not equals. If it doesn't equal -1, then we can say this value was found. And if it does, whatever. Yeah. And we can say something like, and the value was found at index. And what we can do is simply just call our function again, really. You just call it again. Now, realistically, you wouldn't want to do this. And I'll show you what we would do instead. But you could actually just call it again, and it should return the same number. So let's actually see this. Okay, so this time it wasn't founded, right? It did not output this thing, so that's telling me it wasn't found. Let's do it again. Okay, that's 2 times getting unlucky. Interesting. Maybe something's going wrong. Could be the case. Could be the case. Because why would it equal -1 every time? Let's try maybe 1. Does really none of them equal 40? I could just be getting very unlucky, which is super possible. Yeah, none of them equal 40. So let me try it again. There we go. Yeah, I guess we were just unlucky. So it says the value was found at index. Oh, I spelled index wrong, but that's fine. At index 3. So let's actually double check this. Index 3. Yep, we have the value 40. So of course this would only ever give you the first value found, right? There might be another value 40 later on in the array, but it's not going to worry about that one. It's just going to worry about the first one it sees. Let's actually try this a few more times. All right, so we have, it says it was found at 74, so if I go to index 74, yeah, I can see it right here. At 40 again. And not found this time. This time it's found at 24. 40. So yeah, it's basically as simple as what this code is essentially doing. You only really need to worry about this part right here. It's just taking element by element and just comparing it, saying, does this match 40? Almost like you would, right? If you just imagine yourself, you could say you had a list of numbers and you got to check if one of them are 40. So you have the key in your brain, 40, you're thinking about it, and you're just looking at each number. Does that equal 40? Does that equal 40? Does that equal 40? And if it does, right, then you return which, maybe there's a number right next to each in order to order each of the numbers, right? So it goes from 0 has the value 24, 1 has the value 78, right? And so you just tell them, okay, I found the number at line 30, right? So that's like what you would do. But if you don't find it, you're going to say, no, I didn't find the value, right? Which is possible, right? It could not exist. So that's kind of basically linear search. Any questions on that? Okay. All right. So binary search is a bit more complicated. Now, the first thing you have to know about binary search is there's one condition. You can't use binary search unless your array is ordered, either in descending order or ascending order. It doesn't really matter. It just got to be ordered somehow. And so, in order to do binary search, obviously we have to have an ordered number. So can we do that? Let's see. What I'm gonna do. Let me first draw like a little thing about what's going on in binary search. So let me do this. So binary search, what it does is basically, instead of guessing from the first and just going one by one, what the goal is to do is to try to eliminate, whenever you guess one by one, obviously, you eliminate one possibility at a time. So at the very beginning, there is 100 possibilities. In this array that we have, there's 100 possibilities that for where the key could be, right? And when you look at the first one, right, if the first element in your array is not the key that you're looking for, then now you have 99 other left possibilities that are left that could be the value you're looking for, right? So what a binary search is basically trying to do is to basically do that a lot quicker. Instead of after the first comparison, it actually wants to get rid of half of the options, right? So if you can imagine, right, let's say we have an array right here. Let's say we have an array and it's ordered from maybe 1 to 1,000, something simple. Actually, let me check something really quick. I'm not sure if I need to add another. Is it possible? There we go. Cool. Nice. Okay, so let's say we have an array and it's ordered from 1 to 1,000, right? And let's say it's I don't know, it's 100 elements. So let's say we cut. What the program's going to do is it's going to cut right here. It's going to get the middle element. Now, if it's even, right? So we have 100 elements, which I guess means it's even, right? It's always going to choose the left one, right? It's going to choose the left when it comes to the middle, the very middle, there's 2 at the middle, it's going to choose the left element, right? That's just not like you have to do it that way, but that's just kind of the default what everybody does. So we choose the left element, which is going to be 49. That'll be element 49. So at element 49, this is going to be I equals 49. Let's say our key, by the way, the key that we're looking for is 300, right? So at element 49, we find the value 632. Now, obviously, this is not a match to 300. So what do? Well, we now know that not only is this not a match, but none of these are going to be a match because these are obviously greater than 632. And anything greater than 632 is not going to match our key, right? So that's kind of like the idea. And then eventually it'll cut over here. It's going to cut over here. And it's going to take element. Well, what's the middle of this? The middle would be 25, but in reality, I-24. So index at I-24. That's going to be our new middle, right? And we're going to, let's say we have the value, let's say here we have the value, right, 243. Okay, this is obviously not a match, but anything below it is also not going to be a match because anything less than 243 is not going to match 300. So then we look at the middle of this, right? And let's say this is I, well, this will be I plus 2.12, so 36. So this would be I equals 36, right there. And let's say right here we find the value 300, right? That would be pretty fortunate. So then obviously here we have a match, and then this is where the program would stop, obviously, once you have a match. So you can already see this is kind of crazy. This is really fast because we only did it in 3 guesses, right? So in 3 guesses it found it. Whereas if you did this in linear search, at I-36, that means that you've already basically compared this 37 times, or 36 or 37 times, right? And so we're already kind of seeing that this binary search kind of beats that by 10 times. It's 10 times more efficient. And not only that, actually, the larger arrays get, the vastly more efficient the binary search gets than linear search. So, to give you a little perspective, even, right? If with a million size array, you can actually find the number within only like 20 comparisons or 20 guesses. As opposed to like binary search, or sorry, linear search, which on average would take about 500,000, right? So there's actually a few values we have to keep in mind during the whole time. So actually, let me clean this all off. So the main first value we got to worry about when we're first doing this binary search, let's make it our array again, is we have our first value and our end value, right? So we could probably call it, we'll have our, well, sorry, not first value, but first index and end index. So we'll call it first index, and then we're going to call it end index. Now our first index is obviously at the very beginning of our program, it's just going to be 0, right? And the last index, let's say that we have an array of 100 size. So our last index is going to be 99, right? And let's say the values range from 1 to 1,000 again. Okay. And let's say our key is equal to, we'll say 630. And of course we have our middle index. Now, we have to be able to calculate, right? Because our array may not always be a size 100. So we actually have to calculate what's the middle of our index, right? So the way we calculate the middle might seem a little counterintuitive, but the way we do this is not simply because we're just trying to be complicated, actually. Because if you look at it right now, you'd say, well, what's the middle index? Well, it's simple. You just get 100 and divide it by 2, right? So we have 100. Actually, it would be 49, right? Right. Let's get the last index, right? Yeah. You would just say 99 divided by 2. That'll give you 45.5. Drop the 5. Sorry, no, it would give 45. It would give you 48, actually. Oh, yeah. Sorry, actually, you wouldn't do 99 by 5. What you would do is you would say 100. You would do 100 divided by 2, which will give you 50. And all you got to remember is that that'll give you the 50th element. But the index for the 50th element is actually going to go become 49, right? Because we, of course, in computer science, in an array, you start counting from 0. So index 49 will actually be the 50th element, right? So you think, oh, it's just that simple. Yeah, well, not always. Because we're not always going to calculate the element, the size, the middle element, using 100. And that's the problem here. So what we do instead is we say the middle element equals the first index, we're going to say first with an F, plus the end index with an E. We add them together, and then we divide that by 2. And in the very beginning, this is simply going to be 0 plus 100, which is going to be exactly the same as this. Oh, and then I think we also have to say minus 1, right? So minus 1. So in the very beginning, we can see we have 0 and 9. Oh, actually, my bad. And this one is going to be plus 1. There we go. Plus 1. Should be anyways. So we have first index, which is going to be 0. And then we have end, which is going to be 99. Well, 0 plus 99 is obviously 99. And now that I think about it, I think I'm missing it around. Actually, one more mistake. It's not like that. It's actually supposed to be like this. There we go. So it's the first plus the end plus 1 divided by 2. There we go. So then we have 0 plus 99 plus 1. That's going to give us 100 divided by 2. That's going to give us 50. Yeah. And then we're going to say minus 1, I guess. So we'll add another minus 1. That might be a bit more complicated than I needed to make it, but it is what it is. Plus 1. Or sorry, minus 1. So that'll give us the middle index, which is at the moment 49, right? Now, we go to the middle index here at 49, and we get the value. Let's say we have the value 460. Okay, that's not going to work for us. But first thing we can do is we can cut out everything, including that index. So now we've ruled out everything from index 0 to 49 has been erased. We're getting rid, not erased, but like we're ruling it out. Now, what's left after 49? The next index after 49 would have to be 50, right? That's the next index. So what we're going to say is that first index, we actually have to change the value of the first index. We have to change it, and we have to say first index equals, we're going to come over here, we're going to say first index now equals middle index plus 1, which is going to change the value of our first index to equal 50, right? Because middle is 49 plus 1 will make it 50, and that's what we're going to now assign our first index, okay? Now we have to recalculate our middle. So what we're going to do is we're going to say 50 plus 99 plus 1. That'll make it 150 divided by, 150 divided by 2 will give us 75 minus 1 will give us 74. Sounds right. So we go over here now to index 74. And the value that we find is maybe going to be, it's going to be 700, right? Just over. And that's obviously not a match, but we can rule index 74, and we can rule all the way to 99 out. So we're going to cross this out, and this isn't good either. So now we're going to reassign end index, right? So we're going to say reassign end index. So end index now equals middle minus 1. Middle was, or is right now, currently 74. So now our end index is going to end up equaling 74 minus 1, 73. So end index will equal 73. So now we have to, of course, recalculate our middle. So what we're going to say is we plug them in the numbers, 50, 73 plus 1. That'll add up to 124. 124, which divided by 2 is going to equal 62, and then minus 1 will equal 61. So now we're at index 61, right? So we come over to 61. And let's say we have right here at value 61, we have 510, right? So now we cut everything off from here, including 61. So basically every time you cut off the front, you got to reassign the first value, the first index. Whenever you cut off the end, you have to reassign the end index. And every single time, we always have to recalculate the middle. So now what we'd have to do is we would reassign our first index. So our first index is now going to be 62, because 61 plus 1 is going to be 62. So we're going to reassign that to 62. And then we're going to recalculate our middle. So we have 62 plus 73 plus 1. That's going to give us 136. Then we're going to divide that by 2. That'll give us 68. 68, and then we're going to minus that by 1. So that'll give us 67. So 67 is now the new middle we're going to go to. Now let's say we get the number here, 630. At this point, what we're going to do is we're done. We say we have a match, and we would return the index. So we return 67 at that point. And that's basically the gist. Any questions on this kind of the way this is working so far before I go on to the actual code?
I feel like I have a question about the complexity of 0 and how this mathematically fits into I guess fits into like the the actual like logarithmic graph, because I kind of see how this is kind of all going, right? So like it's obviously some kind of graphical thing that is being calculated, but we don't see it. And
Right.
so that's kind of like, I guess there's a question there that I don't really know how to ask yet.
Are you asking like
Does that make
what's the
sense?
efficiency of it, maybe?
Yeah, I guess so. I guess that's where it would be tied back in,
Yeah,
right?
no,
So like on a time graph of some sort.
the efficiency, I guess. Yeah, right. So like, I guess if we look at it like this, if we had our graph here, right? This is the comparisons, and then time, right? Over time. The amount of comparisons, which is bad. The more comparisons you have, the worse, right? So the amount of comparisons over time, I don't know if I actually want to do that. Amount of comparisons over time, I guess that's fine, right? For linear search, it's going to go linearly, right? Just going to keep going up. That's not exactly true. I would actually say, sorry, no, the comparisons for size. The amount of comparisons over size. So obviously, your computer is always going to execute these the same way. What you can kind of think of comparisons, the amount of comparisons is the amount of time it's going to take, right? Because the more comparisons you have to do, the longer your program's gonna last, right? So time it takes, right? And then this is, you can think the size of your array. Size of array. So for linear search, it's going to increase linearly, which actually isn't bad, right? Nobody would ever, a lot of people, nobody would ever really complain about efficiency n, right? Which is linear. But the amount of comparisons over the size of our array is going to kind of go like this, right? So what it's really going to be is this is time. We call it time complexity, which is just the how fast, how long your program is going to run as the size of the array gets bigger, size of the data gets bigger. So we call this time complexity. We call it big O of n. So that's time complexity n, which isn't bad, right? However enemy elements you have is however long it's going to take in terms of milliseconds or whatever, something like that. Now, size of the array, sorry, for binary search, it's going to be time complexity of the square root of n. Now, if you were to put these two in a function, right, the square root of n, obviously, it kind of goes fast in the beginning, but actually over time, it starts to go slow down tremendously, like hardly anything at all. Until the point, or if you know the famous thing, I think there was like, if somebody always says, if you try to put 1 grain of rice on the first chess piece, the first square on a chess piece, and then you double it on the second one and double it on the third one, and you keep doing that over and over again, that's obviously going to explode into a huge amount, right? So the opposite is here. The opposite is happening here. It's obviously getting slower to an incredible degree, because obviously it's like the reverse of being squared over and over again. It's being halved over and over again, right? So that's kind of what's going on over here. This is what you would call the efficiency of binary search in terms of against what's it called, n, right? Which is incredibly fast, right? Binary search is very, very few comparisons, so it would really take hardly any time. Make sense? Does that kind of make sense what I'm trying to say?
Yeah, yeah, it completely does.
Okay.
And thanks for clearing that up. That helps me visualize
Yeah.
kind of like what's going on behind the scenes in so many
Right.
regards.
Right. Okay. So let me. Wrong one. Okay. So now let's jump back to actual code. How do we actually implement this? So let's first create a function called binary search, and then we'll call. Of course, you always need your int array. You're gonna need the same stuff. Let's just copy it. So of course, if we don't, we want to have our return 0, or return -1, because we're gonna get that out of the way. That'll be in case we never find it. Now, what we're gonna type now is all the code necessary to find it, right? So first thing immediately, we just want to basically translate this into code. So if we think about it ourselves, where did we first start? Well, we first started with the index starting at 0, the first index starting at 0, and the end index starting at uh uh the end, the size, right? The size -1. So that's the first thing we could do. We could say first, we could create two variables called first index, and we can set that equal to 0, of course, because that's what it's going to be. Actually, let's put a comma, and then we'll have end index. And we're going to say equals size -1, right? And then let's create right here int. Actually, the middle you don't want to. We just want to create the middle, but we don't actually. So actually, I could just put it right here, middle, but we don't actually want to initialize it yet. Now we're going to. Did they do it with? We're going to create a small boolean actually here. Boolean. Is it a boolean? Yeah. Yeah. Yeah, found. Yeah, found. Boolean found. And we're going to say that found is false, because that's what it would be in the beginning. In the very beginning, before you've even searched, you obviously haven't found something, right? So Boolean found is going to equal false, right? And what we're going to do is we're going to create a while statement. And the condition is actually going to be strange, and I'll explain the condition in a minute. But obviously found isn't there. So basically, while found equals false, right? Found equals false. So this is one way to type it really quick. You can say while found equals false, like that, or you can say it like this. You just have an exclamation point, which basically says while found equals false. So we'll put the exclamation point because it is quicker. And we're also going to add something to this. We're going to say and first index is less than or equal to middle or end index. Now, the reason we have to check this is there's a possibility, of course. Let me there we go. There's a possibility, of course, that our index is not in our array, right? And the way we know this is that if you look at it, the whole time that you're doing this binary search, the end index is constantly getting closer this way, and the first index is constantly getting closer this way. They're constantly going towards each other. They're narrowing down the possibilities, right? Kind of creating this squeeze. Well, if you get to the point, right, that you're looking at like the last one, right? One of them keeps going, right? Eventually, if your element that you're looking for is not in your array, what'll happen is that one of these values will count past the other. So either the first index will pass, right? It'll go past the end index, or the end index will go past the first index. When that happens, right? Of course, that means you've searched all the elements, right? Right? Because you could think of this line right here, the line that before the arrow, as everything that's been searched. Well, whatever's before the arrow coming this way, we can see has been searched, and whatever's coming this way has also been searched, right? So everything's been searched, and they've now crossed each other, right? So at that point, you know, we don't have our this array does not have our element, and when that happens, right? You know, that's how you're gonna you have to stop your loop, right? So what'll happen is found will actually end up equaling true, right? At that point, it is possible that found equals true. Here we go. Equals true. Which if you only make your while loop, if you only made your while loop focused around the found, then your while loop would end up still running. It would keep running, right? But because we add this in here, that makes sure that you're not going beyond and trying to search stuff that doesn't make any sense, right? Like they search stuff that you've already done. So the first index will kind of basically this basically thing saying while index first index is less than or equal to index 1, keep running the thing, right? That's okay. But as soon as these two pass each other, basically being first index becomes greater than the end index, that's when we know, okay, we've gone too far. There's no more elements to search, and clearly we just haven't found our key inside of this array, right? So what we want to do is that's going to be our condition, right? So now at the very beginning of this, obviously we just want to make our middle now. We have to calculate our middle, okay? And we're going to say our middle equals first index plus end index plus 1, right? Which is exactly, oh, actually, I forgot it. I got to take this off, right? So that was exactly what we had over here in our thing. We had first plus end plus 1, right? Then we divide this whole thing by 2. And we want to make sure you don't not technically have to, but I like to always add extra set of parentheses to make sure I know which math is happening first. And we're going to say plus 1. So we have middle, first plus end index, plus 1, divided by 2, and then add 1 again. So that always should give us the correct the correct middle, right? Now what we can do is we have to check, right? We have our middle index. All we have to do is simply say if we're going to say array. We're going to call our array, and we're going to say array at index middle equals the key that we're looking for. We're just going to say, oh, whoops. We're going to return middle, right? Because that's the index we found it at, so we're going to return the middle. Now we can say else if array at middle is actually less than key, okay? So let's say the value we found is less than the key. So if it's less than the key, then that means we got to cut off the back, right? We got to cut off the end, the end, which means now we have to reassign it. So we're going to say end, end index is now going to equal, let's look what we said our thing was. It says whenever we cut off the end, right, we say end index equals middle minus 1. So we're going to say middle index minus 1. And then, yeah, that's it actually. Oh, and also we actually want to say that as soon as we found it, we would say found equals true, right? Okay, so really shouldn't make a difference because the return statement would just quit the whole function, but still. Then we have another else if, and we can say if else if array at middle is less than, sorry, not less than, but greater than the key now, we are going to say that we have to cut off the first. We have to cut off the beginning of our array. And so when that happens, we have to reassign our first index. We're going to say first index equals middle plus 1. Right? Because that's what we had written over here. First index, when we reassign it, we say first index equals middle plus 1. And that should be the whole thing. I'm trying to make sure that that is, but yeah, I think that's the whole thing. Well, let's test it. Let's test it. So now let's come down here. And really the only thing we need to change is instead of linear search, we can just say binary search. And this should still work the same way, right? We both built these functions to basically do the same thing, just have a different algorithm. But basically they both take the same parameters. And they'll return the same result, -1 if there's no match. And they'll return an index if there is a match. So let's see this in action. Let's run it. So it says, seems like there was no match, and I just want to make sure. Whenever you're do stuff like this, sometimes you just have to make sure manually. You want to make sure your program's actually running correctly, so you have to actually verify there's no 40. And sure enough, there's no 40. There's no 40. Let's do it again. Again with no 40. Okay. No 40. Okay. And okay, now we have one. Okay, good. Getting worried there. So it says the value is found at index 51. So 51 is right here. And exactly correct, right? So I believe actually getting index 51 would have taken the most amount of comparisons possible for this binary search. So interesting. No, would it be second most? I think second most, but that's still quite interesting. Okay, so let's actually put it in a little bit more perspective just to see how many comparisons are happening. So we could say, let's do this. Let's say for our linear search, we'll run both of them at the same time. So we can say linear search. We can put a cout statement. Every time we do a comparison, we can say cout comparing array, whoops, array I to, and then key. And then we can say and now. And then the same thing here. Every time we do comparison is right here. So we say, let me just copy this actually. Except here we have to put middle instead of I. Middle. Comparing array middle to the key. And then we say end L. So yeah, so let's do this. Now we're going to create 2 of these. And one is going to do linear search. One's going to do binary search. Ah. Interesting. Okay. I don't know why I did that. I forgot to do one thing very clear. This has to be in order. I don't know. I'm actually surprised it even found the value. It found the value of 51 somehow. Which is lucky. But this array has to be in order. So actually let's make sure that it is in order. So instead of doing random numbers, what we're going to do, we're going to say, let's do numbers between No, we'll just do it ordered. Okay, so we'll say something like... Actually, that's a brilliant idea. There we go. We'll make it between 5. We'll make it between 5. So basically, this will generate numbers between 1 and 5. But what'll happen is whatever number we get here, we're going to multiply by I. Multiply it by I. Right, so we'll get some random number between 1 and 5, and then we'll multiply by I. So these should be getting increasingly larger every single time. There we go. Yeah, that should work. That should work. So let's do... Let me make sure I'm not doing something stupid, because that's possible. 5 times 2 equals 10, but 5 times, or 1 times 3 equals 3. So that is stupid. Yeah, I can't do that. We'll just do it like this, then. We'll just say plus 1. A little boring, because it's going to be super easy that even we could find it in faster time than the linear binary search, but that's okay. So let's actually see this. There we go. So did we even find it? Did we even find it? The value was found at that. Cool. Well, actually, that's interesting. What happened here? What happened here? Let's look at my array. 1, 2. Okay. So something went kind of strange here. Compared 752. Compared 52. I'm very confused by that. I think I may have messed up one thing. I'm also confused by my linear search. I don't know why it's comparing. Did I run my linear search twice? No. Huh. What did I do wrong? Let me try that one more time. Where is this coming from? Hello. The value is found at that. Let me do that here. Not sure why it's printing it twice. It's printing the whole search twice. Okay, let me try that one more time. It's very strange. Okay, well, I've found there. Um. Okay, first let me. Linear search is acting up weird. Well, it's actually doing it fine. It is doing it fine. We can see that it's doing about. What you can basically assume is that it's comparing it 40 times. I don't know why it's printing this whole thing twice. But it is doing that. I just want to make sure what happened with binary, because binary didn't work for some reason. Let me relook at our algorithm. This is the problem. It should be -1. That's why. Our calculation for the first was wrong. And also, if middle array is less than, then that means we gotta cut off. Oops. This should be first. This should be end. And we gotta switch these. Plus, minus. There we go. There we go. Okay, so obviously this would be when key is greater. If key is greater than the middle, right? So if key is somewhere, this is the middle right here, but key's over here somewhere, we got to cut off the front, right? Which is what we're doing here. So key is greater than the middle, so we're reassigning the front. But if it's over here at the end, we cut off the back and we reassign the back. What is going on here? So this should work now. Let me actually save it though. There we go. Yes. I'm very confused where this extra though. Okay, so this is very. I'm not sure what's going on at the moment, but we have our our binary search here where it checks 50, then it checks 24, and then it checks 36, and it keeps checking until it gets to 40. Right? That's our binary search. It took about 7-ish comparisons, as opposed to our linear search, which took 40. I have no idea why that's printing there. This like 40 comparisons. It's because of this. It's because of this. I should have not done that. Okay. Let's make it. This is exactly a good situation why you'd want to save those values. So let's say we did it right here. Let's say let's just binary search. Actually, we'll say something like, yeah, we'll do this. We'll say int b search equals that, and then we're gonna say b search. Copy that there, and we'll do int l search equals that. Those other functions were just repeating the linear search again. That's what was going on. So instead of that, we're going to put that there and this there. And looks good. This should work fine. All right, so we can see. Let's open this up. Linear search took all of these. These are all the comparisons, right? Even more. Binary search just took this, right? And so they both find it at the end of the day, but one is clearly faster. All right, that's kind of basically it, right? That's the gist of the binary search. Any questions on any of that?
Not really. I'm just gonna have to go back and work on this a little bit. I had some weird it was a weird problem that said I was expecting a declaration to be declared at the beginning, and I went back and put return -1. It's basically at the top, at the
Uh-huh.
top where you started the linear search. So
You
what do
can
I?
show me if you want to show me real quick. I can see real quick.
I'll just scroll up. Let me see what yours is doing real quick because it might just be it's probably just the spacing all the way to the top, like right there, basically where it says return -1.
Right here.
So yeah, I don't know why, and it keeps telling me like I'm just expecting a declaration.
Expecting the declaration. And this matches
Oh
exactly.
nope, I didn't put the C out. That's what it is. But everything else matches. Yeah, I just don't have the C out, which that shouldn't really do anything. That shouldn't
Yeah, I
change.
shouldn't change anything.
No.
I can check it out real quick if you want to see. Let me see what you got. Let me, oh, shoot. There, you should be able to share now. I'm expecting a declaration. Oh, yeah.
Yeah, which then it throws off everything. It's further down. But if I just remove it, I have to remove that, then it goes away.
Oh, no. Wait, what? Yeah, this is very strange. Add another, because I thought this might have been a bracket issue. Try to build that real quick. See what would happen. It's
All
very.
right.
Oh, let me stop.